Yeah, okay. So, welcome back to our lecture about virtual prototyping. So, last time we stopped with the topic of primitive channels, and we learned that there exist already some of those, and they interact always with the SystemC kernel. Yeah, so you remember this delta cycling loop where we have the evaluate phase and the update phase. And in order to understand how that works, we implemented last time a custom signal, which I will just continue today. And there are actually three things that we have to acknowledge here is that we have to send an update request. So our signal will tell the SystemC kernel, hey, somebody wrote to the signal, we want to update it later in the update phase. And then we have to implement the update function, and we also have to implement the default event function. So let's go back to the source code again. And we have to remind us what we did the last time. So I will switch the display. Okay, so now you see again VS Code. So can you read it, or should I increase the font size? Is it okay, or yeah, okay. Yeah, so it's kind of a weird bug here. What's going on? Just close it again. Here we go. So that's what we built the last time. We created an interface. So we always do these pure virtual classes to define an interface, to define a read function and a write function, and it's always templated. So the interface could be from any data type. So it could be integer, but it could also be a SystemC unsigned data type or whatever. So that's the reason why we template that, and the read method will return the value that we read from the signal, and there's the write method that writes a value to a signal from this type T. Okay, but that's the interface, okay? So let's continue. What's now the signal class? So the signal class is derived from that interface, but also from this prime channel class. And because of that, we basically interact with the SystemC kernel, or we can interact with the SystemC kernel. And then we have two variables. We created that last time. So we have the current value of the signal and the new value of the signal. So this is when we want to update it, basically. In the constructor of this signal class, we just reset these values to 0. Could be also, if we use, for example, later on a SystemC type, this could also be undefined or something like that. But right now we just take 0. The read function is pretty simple. So we just return the current value. The write function is a little bit more complex. So the value that we write here as a parameter, we will first write into the new value variable, or member variable. And if they are different, and that's the semantic of a signal compared to a buffer, only if they are different, we will call this request update function. And this request update function is implemented in this SC prime channel. And this will interact with the kernel. So request update is basically then going into the kernel and is saying, hey, there is an update in this class happening. And later on, we want to, when we go to the update phase, we want to perform this. So that's the delta cycling. So here we are interacting with the kernel, and also the kernel wants to come back to us, and therefore we have this update function here, which is basically a callback. So when the kernel makes a transition into the update phase, then all the processes that are basically requested an update before will be updated. And then the current value will be set to the new value. But also here only if it's different. And this has the reason why we check this again, also because of the semantic of a signal. It might be that you set it and then you reset it again and so on and so forth. So we make sure that in any case it's only updated if the value is different. Because we only want to create this event here, the value changed event, which we have defined here. So we only want to notify this if the value change really happened. Yeah. So, and that's basically where we stopped the last time. The third thing is you have to implement this default event function, and there you just return this value change event. So it's basically just returning a reference to this event. And this is important because we want to use that in sensitivity lists. Yeah? So that's the signal class, but let's use this class now. So let's build a system out of this. So we create again a SystemC module, which we call producer. And this producer will have now a port, SC port, from our type signal. And just keep it easy, let's just use integer as the value for or the data type for the signal. And then we give this port a name, I don't know, output or something like that. Then we want to have a process. And this process should be executed as an SC thread, so therefore in the constructor we will make a SC thread out of this. And now what is the semantic of this producer? So it should write at the beginning of the simulation the value 10. Then it should wait for 10 nanoseconds. And then it should write 20. We can wait, also 20 nanoseconds, doesn't matter. And then the simulation should be stopped. And you can stop the simulation always if you call SC stop. Yeah. And then we have a consumer. And the consumer will now use an SC method. But first we need also a port, SC port, and again we take our signal from type int, and we call that input port or input. And then also we have a process that just reads from the signal. So input, not slave. And then we just do read. And then we just print out the value. Or we can, maybe we do it like this. So we say add sc_time stamp. That's this helping function that tells us the time. And then the value is v. Okay, so now this process is not yet triggered, so we have to define that. We do that again in the SystemC constructor for this module that has the same name. And we make process a method. And now we use the sensitivity list. That was our actual goal. So if we use the standard SC signal, we can just use a sensitivity list to be sensitive to the change of a specific signal. But now, since we implemented our own custom signal, also that works here because we have implemented this update request and update function and the default event. So we write here sensitive. Then use the streaming operator, and then now we are sensitive to the input port. So that means every time there is a change on the input port, this method should be called. That's the semantic. And we can also specify this function. It's, I think, also a macro, and that tells basically that in the beginning of the simulation, this registered process will not be called, so it will not be initialized. Because I can show you later on, if I just comment it out, then you will see that in the beginning of the simulation at time 0, we will get some output, and we don't want that, so therefore we use this don't initialize thing. Okay, so what can we do now in the SC main? We can just create an instance of the producer. And all modules need a name. So we give them a name. And now we create our signal of type int, and let's call that just channel or whatever. And now we have to bind it, so now we can say pro1 dot this producer, so it's output. Yeah, that's how we called it, output. And now we bind this to our channel. And also here, consumer input, we bind it to our channel, and now everything is connected. Yeah, so we really built this system here. We have here our output port. So this is the Pro1. This is our channel, yeah, which is our custom signal of type integer. And this is then connected here to this module, which is the consumer 1. And this has here the input port. Yeah? This is what we now build. Well, okay. And then we can simulate that for 100 nanoseconds, for example. And if it was successful, we return 0. So I hope that this still compiles. You never know. Okay, so something happened. So at the beginning, we write 10, then we wait for 10 nanoseconds, and then we write 20. And then at that time, it's 10, so it makes sense. So we get this. So probably it would be better if we do it that way. So at time 10, we write the value 10, and at time 20, yeah, if you want to have time 20, we have to wait for 10, because 10 plus 10 is 20. Then we want to write the value 20. So if we just run it like this. So at 10, we get now the trigger here, but why are we not? Okay, makes sense, because now we immediately call SystemC stop, and then it stops the simulation, so we need another wait 10 or whatever to get this done. Yeah, so at 10 nanoseconds the value is 10, and at 20 nanoseconds the value is 20. Yeah, and every time we call this write function, and then we go basically to wait, so we go back to the SystemC kernel. This is basically then when this transition happens, yeah, from the evaluate phase to the update phase. So this is basically the evaluate phase when we write this, and then we go in the write phase, we request the update, and then if all functions or all methods and threads are evaluated, then the SystemC kernel transfers to the update phase, and in the update phase, basically all the modules, or in this case the signal, all these signals are called again with the update function here, and then the actual value is then written, and also the default event is fired, and all methods that are listened to this default event on the sensitivity list get basically then triggered. So all processes that are sensitive to this get triggered. That's the idea. And that's also how this SC signal works. Yeah? So, but we build our own custom signal now that you understand the mechanism behind it. Yeah? Okay. So let's go back to PowerPoint. Yeah. And this is, as I said, this is usually an exam question, so you should understand what is update request doing, or request update, update or default event. So how is that basically interacting also here with this discrete event simulation kernel? Yeah, so that's basically again the idea. So for the evaluate phase, there we call these request updates. Yeah, so this is the call to the SystemC scheduler, and the scheduler internally has a queue that basically stores this request and then handles it basically later when we go to the update phase, and in the update phase we call then all these update functions. And they may then fire this event, and they get access to this event, to a pointer to this event basically by the default event function. And this default event function basically is always called if you use here the sensitivity list. Good. Questions? Or is it clear? Okay, then let's proceed. Another topic, so-called hierarchical channels. Yeah, so the primitive channels are derived from this SC prime channel, and they are usually passive, so not really active. And hierarchical channels are derived from SC module and can be active. So it might be that you build a system like this, and the channel is not only like here, for example here, it's not just a passive thing that has two methods for read and write. It could also be that if you derive the channel additionally from SC module, that you probably can have also a thread here. And then you can build a complex bus here that also has, for example, an internal thread that handles an arbitration of the bus or does any scheduling or something like that. And then you can have threads and methods internally, and they can also be composed out of other SystemC modules. So you can really build a hierarchy inside. And this concept is heavily used in transaction level modeling, which is basically the next topic of the lecture, I would say. Usually the hierarchical channels do not have the evaluate update mechanism because that doesn't match to the semantic of TLM, but you will understand that later if we talk about the concept of TLM. Some additional things about ports. You can have port arrays also and multi-ports. And let's first talk about the arrays. Let's first talk about the array. So what you could do is you could describe a module like this, and then you have an output port, output 1, output 2, output 3, or whatever. But this is not really convenient. You can make this with an array. That's much smarter. So you just create an array of ports, and you get the same thing, actually. Another thing that you could do is using so-called multi-ports. Then it's actually only one output port, but you can connect several channels. This is also sometimes helpful because it's dynamic. So here you can add, at the runtime, you could basically ask the user how many channels you want to connect, and then you put in 3, and then your simulation is created with 3 instances of channels. If you use port arrays, or you make a fixed amount of ports, then it's static, so you cannot change that during the runtime, so it's fixed on compile time. So how does that look like? So first of all, port arrays. So you could write it like this. So you say this is port 1, port 2, and port 3. But this is very often too complicated, so you just say, okay, I want to have an SC port from the SC50 out interface, and this should be an array with 3 elements, and then you get your 3 output ports. So that makes it pretty, let's say, convenient. So how do you access this now? For example, this is again a producer module. This has a thread, and the thread you just iterate here, and you write the number 2 to the port, and you can address the port now like an array. So you start with 0, and then you end with the number 2, and then you send to each output port basically the value 2, and then you wait. And this happens basically, this for loop happens then concurrently. The wait is inside. So then it's not concurrently in that sense. So basically you write the 2 to the first port, then you wait for 1 nanosecond, and then you write 2 to the second port, and then you wait for 1 nanosecond, and then you write to the third port basically. If you would put the wait outside of this loop, then it would happen concurrently. Yeah, how do you connect this? Also the binding, you just address it with the array operator. Yeah? So also I think straightforward. But this is static, so you create that at compile time, so it's only like you wrote it in the code, it will be compiled. You can also template this. This is also interesting, but this is still static and at compile time. So you can say your module will have n ports, and then you can just use the n here. So this is just typical C++ templating. Yeah? And it's actually the same code, but of course you have to make sure that if you instantiate then your module and you put 3 here, that you also bind all of these ports. Yeah? But you have to manage that on compiled or before you compile to make that correct. But the rest stays the same. Yeah, and multi-ports, that's now the dynamic thing. So then you create an SC port, and now you use some additional template parameters. For example, 0 or more bound. That's helpful because there you can say, okay, it's also okay if you do not bind anything to that. And yeah, you can, maybe I have to start here basically. So you instantiate your module here, but at this time it's not clear yet how many output ports do you have. And you have now, for example, here 3 FIFOs instantiated. And now you bind them. And every time you bind it, internally there is a counter that counts up the number of ports. Yeah? So for each binding operation, you count that up. And you can access the number of ports with this operator here. So port.size gives you the number of how many ports are actually created. And that makes it pretty convenient. Also to make this flexible, because this is now dynamic, so you can do it during the simulation. Yeah, so for example, you could ask the user here, how many ports do you want? And then you create in a for loop, or you create some instances or an array of FIFOs, and then you bind this array of FIFOs to the ports, and then you start your simulation. Yeah. Also that is possible. But actually it's only one port, and the port itself basically manages that for you, but you have to say that this is important 0 or more bound, so that you can bind more. But you access the port also again with the same operator like in usual array. Yeah, yeah, multiple bindings. Yeah. It would work in general, so SystemC would support that you can say you connect basically 2 modules to 1 channel. So in general that works, but SE5 and SE signal are implemented in a way that they can have only 1 writer, because that's the semantics also like in Verilog. There can be only for a signal 1 driver. And yeah, it also makes sense from the perspective, because otherwise you cannot synthesize this in Verilog, and therefore they have the same concept here in SystemC as well. Okay, yeah, so let's talk a little bit about events and sensitivity again. I think this is something that we have discussed already. So it's just a repetition. So there is this SC event class, and we used that already with notify, and I think we discussed that. The important thing is that only the first notification is actually noted. So if you trigger an event here, following triggers or notifications are ignored. And if you want something that does not ignore that, you need another class which is called SC event queue, and here you can notify several things then one after each other, but you can also Yeah, here you notify something for 40 and 30, and then in this queue this will be sorted according to the actual time. So even though this notification happened earlier, it will be executed later because this one will be there earlier. So that's the idea of this SC event queue. So you create this basically here, and then in this module you will test this. So this is why we call that event queue tester. So there is a trigger process, and then there is a sensitive process, and the sensitive process depends on the trigger event queue. So every time this event queue fires an event, then this method is called, and they are basically implemented here. So the method that is triggered just gives you the timestamp as output, and here the trigger process just waits for 100 nanoseconds, and then you schedule several events, and here it's basically then just printing out. Yeah? So that's if you need that behavior that you want to schedule a lot of events one after each other. Good. Yeah, channels and interfaces again. We talked about sensitivity already, and there is another topic called event finders, but I don't want to go so deep into that. So if you're interested, you can check this here in the code. We have some special events. So if we write this, then we always mean the default event, and that's the function basically that we have to implement when we write our own signal. But especially for clock, there is another function which is pos. That means this is the positive edge of the clock, because the clock has a positive and then also a negative edge. And sometimes we want to be only sensitive on the positive edge. And to implement these special events, there is also something there. We have to implement this SC event finder, but yeah, as I said, this is not so important. If you really need that, then just look in this example code and then you will understand what's going on. Okay, so let's have a quick look again into the SystemC kernel. So far, all the processes and methods are basically created during elaboration. So what you write down, it's again static. In your code, during compile time, you specify, I want to have this many methods and this many threads. And for hardware, that makes sense, but in some cases like test benches, verification, or if you want to model software or tasks in an operating system, also that you could do with SystemC, then it makes sense also that you can spawn a new process during runtime. And you can enable that by defining this variable before you include SystemC, and then you can, with sc_spawn, you can create a process during runtime. And this also allows the passing of arguments for processes that usually is not there. So very quick example where you can see that. So you have an SC module, and that has a parent process, which is a thread. Then you wait in this thread for 10 nanoseconds, and then you call sc_spawn, and this is basically using sc_bind, and then you point basically to this child process, and then you can also transfer here an argument like the 5. So maybe you want to spawn several and you want to give them IDs or something like that, and then this would be useful. And for each of these dynamic processes, you can get a handle, which is sc process handle as a type here. And then you can also wait for the terminated event here, and then this process will die when all the childs, or in this case there's only one child, also terminated, and then also the parent process will die. And the child process just says, okay, process ID 5 has started, and waits for 10 nanoseconds and then also dies. Yeah? If you want to keep this alive, you need again an infinite loop around this. Yeah? Also, this would be possible. Yeah. Yeah. So basically, you have the handle, and then you can also interact with the process that you just created during runtime. And this can be then, this could be also in a for loop. So you could ask the user, how many processes do you want to spawn? So for example, if you want to analyze what is the, I don't know, when your system starts with congestions, for example, and then you have, again, a producer, and you want to see how many producers will probably saturate the bus or something like that. That you could ask the user at the beginning of the simulation, how many dynamic processes do you want to have? And then the user says 10, press enter, and then you create 10 processes and you do the simulation, and then you get the results. So that's what you can do here. Okay, some other things. Yeah, report handling. There are some special functions to basically format your output of your virtual platform infrastructure. And there are several escalation levels, so just information. You can call this function. If you want to have a warning, then you would use this one. If you want to have an error message, then you would this one. But then an exception is thrown, and here you have to handle the exception by using try and catch. But if you successfully basically handle that, then the simulation also continues. And there is SC report fatal. If you call this, then the simulation is stopped. So this function call will always call SC stop as well. And there's something else which is cool, which is SC assert, and then you can test a signal for a specific value, for example, and if this value is wrong or false, then the simulation is also stopped like this. Yeah. And the cool thing is there is a report handler, and in that report handler you can then basically specify what is actually the output and which level of reports are you interested in. Yeah, so there's an example also for such a report handler. So here's an example module again. Here you do an assertion of two variables. If both are true, then you continue, then you report info, or you make a warning, or here you report error within a try-catch block. And here you call then SC report fatal, and then you see also basically that, okay, the simulation stops, and it tells you the line number as well. And they, in SystemC, they use a lot of macros, and they also internally do some clever things that you get the line number. Yeah? So you could, if you are interested in that, you can check that out. So they do some clever pre-processing basically to store also the line numbers here. And how this output looks like, you can specify. So first of all, you can say you want to, you don't want to log that to the output, you can also log it to a file, which is also then convenient. And then you can say, okay, just show me info and warning, and in the rest I'm not interested, for example. But you can do even more. So you can write your own report handler, which is basically a function. And then you can basically make your own style here. And this is an example that I took here from our artifacts repository, where I get the current time plus the delta time plus then info, warning, error, or whatever. and then the actual info. So you can define how the output should look like. You can format as you like it, that it looks nice. Yeah. And if you then use the report handler here, you can set this function, and this function always has to implement here this report and action thing, and from that you generate the output. Yeah. Okay. Yeah. What else do we have? Which is also pretty convenient in some cases. We have several callbacks that are executed at a specific time when we run a simulation. So when we call SC main, we start with the elaborate phase, and there's a callback before end of elaboration. This is called, before we end the elaboration and go to the actual SC start. Then there's the end of elaboration. Then this is when the elaboration has ended. Then we have the start of simulation. This is here. Their function can be called. And we have end of simulation. This is then at this place before we basically do the cleanup and call all the destructors of the modules. And these callbacks are there for each module and also for each prime channel and SC port. So all these classes implement this, or if you implement them, basically they will be called by the SystemC kernel. So the SystemC kernel knows, okay, this is the list of modules that are there in my simulation, and then the SystemC kernel goes through all these modules and calls these functions at a specific point in time. And this is helpful. So for example, before end of elaboration, you can instantiate further SystemC objects, modules, channels for dynamic things, for example. End of elaboration, when all of this has been called, then we call this. And there you are not allowed anymore to create any more SystemC objects. But you can create dynamic processes, as we have learned before. And so also some diagnostic can be printed here, for example. So then you know what your simulation actually is, how many modules you have, and then you can maybe print out the structure of your simulation. There's start of simulation. So after you call SC start, what you can do there is, for example, you can open text or trace files where you want to put some logs or information. Here you can also still create dynamic processes. And there's end of simulation. When you terminate the simulation with SC stop, then this is called before all the destructors are called for all the modules. So that's a nice standardized way that your modules get called. So for example, you want, when end of simulation is done, maybe you want to close a file that you have opened at start of simulation or something like that. And there you see that there's an SC module. You just implement it as we did it now for many times, and then you can just create these functions, but they are not mandatory, so you can just implement them. If they are there, then they will be called. Yes?
What happens if we use the start of simulation and forget the end of simulation to close a file?
Then, I don't know, then probably this file is never closed. So this is actually the example, right? So here you create a VCD trace file, and here you close it. So if you don't close it, then probably it's still there in the memory and it's not cleaned up. So you created a memory leak. But maybe the operating system will then, I don't know, maybe clean it up for you or whatever. Depends on your system. But you could, if you don't do that, so that's usually a problem in C++. You can easily create memory leaks. So in other languages like Rust or so, you are not allowed to do that from the concept of the language already. Okay, yeah, so that's it with the SystemC base layer. Yeah, so with that we can now simulate RTL type models with signals like Verilog or VHDL. So that's what we actually could do now. So we can now build the virtual model of a chip. Yeah? So one-to-one. So if we know this is the RTL design, for each block that we maybe have in Verilog, we could also implement now a SystemC block that does the same thing. And then we can simulate that. And usually much faster than Verilog. So since we compile everything, the things could also be optimized then by the compiler, and the simulation will be pretty fast. But still, RTL simulation is also with SystemC pretty slow. And therefore, we will talk about some other concepts where we raise the level of abstraction and simulate on this much higher level, much faster, but also with less accuracy. But before we do that, so before we go to TLM, I just want to introduce you also to some commercial tools. So some years ago, the slide here was titled with the market of virtual platform tools is growing. So there was a lot of tooling around virtual platforms. But now some companies, basically Synopsys, Cadence, and Siemens, they acquired other companies. So Siemens acquired Mentor, Synopsys acquired Imperas, ASTC was acquired recently by Cadence, and Symix was acquired by Intel. So some of these virtual platform solutions that built on top of SystemC are now gone, and there are basically 3 vendors that have the usual tooling. So that's the commercial market, I would say. So there's Synopsys Platform Architect. I will show you that in a minute. But there's also some open source stuff still happening. So there's a lot in this QEMU world going on, and there's also Gem5 there as a simulator for CPUs that is also capable to be connected to SystemC. Yeah, but so the real, let's say, open source platform thing for building a virtual platform is still a little bit missing. But there are some small companies in Germany working on this kind of tooling, and also we at the university that we also have in the future some open source infrastructure that is kind of reliable to build a virtual platform. But even though there is a lot of open source and SystemC is also open source, I want to show you a little bit the tool. And I have one example here. This is Synopsys Platform Architect. This is around more than 10 years already, a well-established tool also in industry. And the interesting part of this is that you don't write SystemC code to build a virtual prototype. What you do is, it's kind of a drag and drop solution. So you have a huge list of IP models, and then you just drag and drop your model. For example, here, this is a processor model for a Cortex M3. You just drop it there, and then you connect it to an internal system bus, which is AMBA AHB or something like that. And then you have a model for a memory, you drop it in, and then you connect it. And this is kind of a graphical thing. So you just connect, you do this, what I did on the blackboard here. So you place it there, you connect it, and from this graph that you build, basically SystemC glue code is generated automatically. So you don't have to write all this glue code. This is generated from this. Yeah? Yes.
So can you also use this to?
True. Yeah. So platform architect has also the possibility that you model just parallel software. So you can define tasks, and these tasks are scheduled in a specific order, and all of this. Also, this is possible with platform architect. Yeah. But actually, the idea was to build hardware, but they had several use cases where it also makes sense to model software on a higher level and also connect that to another hardware model, for example. Yeah, so that's one thing. So, but if you now build really the SoC of a smartphone, this is just a simple small microcontroller where you build a virtual platform for. So that's what I built. I think that was even my diploma thesis where I did that. So long time ago. But if you really build a huge system, this graphical input does not scale anymore. And therefore they have a Tcl scripting interface, and I think in the meanwhile also some Python scripting, so you can script basically also the setup of your platform. Yeah, so you can then write a loop and say, okay, I want to have 4 cores, and then it instantiates 4 cores and connect it to the bus automatically. So this makes it a little bit more convenient. But the cool thing is that this is well integrated with all these models that are around. And they have also some debugging tools. So you can just connect your GDB debugger to this virtual core model. And you have the full visibility. So you can always look into the ROM and also into the RAM. And you can see what's going on during the simulation. So you can stop the simulation at a specific point in time, and then you can check in the RAM, oh, is my boot code correctly placed or whatever. Yeah? And also here you see there's the UART interface. So there runs this program that prints here microelectronic, for example. Yeah, so there you see that. If you look into the ROM, you see also here the characters of this ASCII art, yeah. So you have the full visibility, and that's what we want. Yeah. So if we have, for example, just a prototype board, we can just access to all the things that are visible for us through the JTAG interface that the board has, maybe. But here we can look into each model, what's going on. And that's the main advantage of SystemC. Yeah. Yeah, so Platform Architect offers also some other things. You can connect it, for example, also to this HAPS, high-performance ASIC prototyping system, and you can have a hybrid simulation. So some parts of your systems are just modeled in software, but then you take the RTL, put it on an FPGA emulation platform like HAPS, and then you can connect it. So that makes a lot of sense. For example, if this is the model or the module that you are developing, or this IP block you are developing, and you want to test the RTL in a specific context. And the context is then basically simulated in software, and your RTL model is really synthesized on FPGA and is executed there as it would be executed on a real chip. Yeah. So this is kind of the commercial view. Yeah? And I don't want to advertise now Synopsys so much because there are also other vendors of tools, but I worked a lot with Synopsys and I know this tool pretty well. Therefore, I'm showing you that. Yeah? Okay. But now let's make the transition now to transaction level modeling. And therefore, I will go to the next slide set. Just checking again that I'm not skipping a topic. No, that's correct. Yeah. As I said before, so far we can now model RTL level with SystemC. So if you have attended my Rechenanlagen class, you remember Verilog, or back then VHDL when you heard it with Professor Koller, how you build basically RTL models. And now you could do the same also with SystemC. But there's more. Yeah? So that's the big picture. And so far, we talked most of the time now about this block. Yeah? So the base layer SystemC, where we can do RTL models. And now let's move the level of abstraction to this higher level, where we talk about transaction level modeling. So that's the topic now for the rest of the day. And the main question is, how can we really build such a virtual platform, a virtual smartphone? Yeah, so, okay, this is also a little bit old example, but this is built in Synopsys Platform Architect. They completely built, I think that's Samsung Galaxy S3 back then, completely virtual. Yeah? So, and that's really compatible to the actual SoC and smartphone that is built. So you see there are the cores, there's even the battery module, and the battery management system is implemented as a SystemC model. Yeah, so when you change in this, and I tried that out, it's really funny. So if you change here in this battery management system, in one register, the value of the battery to 50%, then also immediately when this is simulating here, basically, then also here the battery will go to 50%. Yeah, so it really actually models the actual hardware. And this is pretty impressive that you can completely virtually model the complete hardware and software running on it. Yeah? And that's interesting. The software does not see that it's executed on a virtual hardware. From a software perspective, the software feels like it would be executed on a real hardware. And this is different to, for example, Android Studio, where just Android is emulated and you can test your apps. This here is much more detailed, and therefore the simulation is also slower than an emulation like Android Studio. Yeah. When we look on a typical system-on-chip architecture today, also maybe in your smartphone, it would look like this. So you have the big cores, you have the small cores, maybe they have a shared cache level, and then there's a coherent memory bus or even a network on chip, and then you have a GPU connected, maybe another video processing accelerator, or maybe also an accelerator for neural network or something like that. Yeah? And then you have an I/O bus where you have your display connected, your USB port, your SD card connection or whatever. Yeah? And then you have the memory subsystem as well, so the DRAM controller and the DRAM that is connected. So the task for you is now basically to categorize the different components that we have here into 3 categories. And from the perspective of communication, so in this aspect. So how would you categorize these different types like CPUs, caches, a bus, or also modules like this here, when you have 3 categories? And think in the context of communication. So which component maybe starts communication? Which component just
I would say the I/O probably starts, so the user makes some inputs and the I/O gives out the signal.
So which one is always starting communication? Which of these components? Yeah, so for example, the CPU, right? So the CPU wants to access the DRAM. It's not the case that the DRAM wants to access something from the CPU, right?
Yeah, but the CPU must know what it must do. So we need maybe first SD card or flash from which the CPU reads.
Yeah, but then the CPU wants to get some data from the flash maybe here. Yeah? So CPUs, or maybe also the GPU, they belong to this category that initiate some communication. Yeah, so even if the CPU has not yet a program that should be executed, the CPU will get it from somewhere. And for example, DRAM memory is always passive. It's just a target. So the CPU wants to have something from memory, or the CPU wants to write something into memory. Yeah? And these are basically these three categories. So you have initiators. These are usually components that initiate communication. And then there are targets, and they are usually passive. Usually they do not start communication. Okay, there might be an exemption here. This is the interrupt controller. So the interrupt controller starts a communication towards the CPU, maybe. Yeah. But in general, we have usually this kind of memory mapped system. Yeah, so each component here has a specific address, and if you address in this range, you will end up in the DRAM. And the CPU usually initiate communication, and these components are targets of communication, and interconnect is usually just forwarding things. Yeah? And this is the basic semantic that we use in transaction level modeling. So we will have modules that are initiators, we will have modules that are interconnects, and we will have models that are targets. And an interconnect is an initiator and a target at the same time, actually. Yeah, because it receives something as a target, like this cache. So the CPU initiates a communication. The interconnect gets this as a target, but then if we have, for example, a cache miss, then also the interconnect component, like the cache, will initiate a new communication. So the initiator is, or the interconnect is an initiator and a target at the same time. Okay, so that's the semantic, how we name modules in TLM. Yeah, and then there's this famous trade-off between accuracy and speed. Yeah? So if we have an RTL model like VHDL or Verilog, or now you know SystemC, they are very accurate because they reflect the actual architecture that we produce for the chip, right? So we take our Verilog model, we synthesize it, we create this GDS2 file, we send that to the fab, and the fab is fabricating the chip for us. So this is pretty accurate, yeah, because this is the input for the fabrication already. But if we simulate that, it's really slow, because we simulate the system as it is in hardware later on, with all these signals and events, and this makes simulation slow. Yeah, so if you have a lot of events, your simulation will be slow. If you have a lot of signals, these signals will have again a lot of events, and you have a lot of interaction back and forth with SystemC kernel and the modules, and this makes your simulation slow. So, and also inflexible. To make a change in Verilog is probably pretty complex. So if you want to test a new cache architecture, it takes you probably 2 weeks to build that in Verilog to get it running, and then you have the results. This takes too much time. So you want to have something where you can just very flexible change something and you get results immediately. And this is an example of an RTL simulation. This is the simulation of a DDR3 DRAM protocol. So you see there are a lot of signals. Somewhere there is the clock of the DRAM. There you have some DRAM commands that are sent. And here this is the data. So you make somewhere a DRAM access and then you get the data out there. Yeah. And you have thousands of signals. And it's also not so easy to debug something on that level. Yeah, but sometimes you are just interested in when communication starts and when communication ends. Yeah, but in RTL you get all the details, and this makes the simulation slow. On the other hand, you have system level simulations which are usually fast. And you have a large flexibility, so if you implement your model in C++, you are pretty flexible. But they can be inaccurate because, as we discussed in the beginning of the lecture, a model is always an abstraction of the real thing. And if we go for system-level simulators, they are usually abstracting things away and get more inaccurate. And this is now the other extreme. So this is RTL, where you have thousands of signals and 10,000s of events, which makes the simulation slow. But you can also build a simulator like this, where you say, okay, if there is a cache miss on this address, I add to my cycle variable just a fixed DRAM latency. I don't know. We just say each memory access is 20 nanoseconds or 40 nanoseconds. 40 would be probably more realistic. Okay. That's fast, so to execute this in the simulator is pretty fast, right? This is just a comparison, okay, a function call, whatever this function does internally, and then you add up latency. But the problem is that DRAM latency does not behave like this in reality. For example, this is for a specific application, I don't remember which one, the latency histogram. So that shows you, this is latency from 50 nanoseconds to 250 nanoseconds. For this application, how often which latency has occurred. And you see that, okay, maybe here 60 nanoseconds is that what happens most. But you miss a lot of outliers. And these outliers usually make the difference and make your application run slower as you would expect. And if you use then a fixed latency model that always says, okay, each DRAM access is 60 nanoseconds because this is the average that we see or most of the time see, then you miss some important aspects and you get wrong results. Yeah. And for DRAM, it's also interesting that the latency also depends on the bandwidth. So in general, you could say that if you plot bandwidth over, latency over bandwidth. So here's your bandwidth in whatever gigabit per second or whatever, and here's your latency in latency in seconds, or here bandwidth in byte per second or whatever, then you will see that there is kind of a linear region. And if you go to this is kind of the maximum bandwidth that you could get in theory. If you go closer to that, you will usually have a latency explosion. So that means that if you use the memory system much more, then also your latency explodes. And this depends on the application that you run. So that's also important. So some applications even have this behavior, or maybe they go already earlier up. So that really depends on the application. And if you model a fixed latency, that's basically that. But this is not the reality. And this is the problem. You need to find always a trade-off. And this is what is showed again here, between the accuracy of your simulation and the simulation speed. Yeah? And these are basically the two extremes that we have. So RTL with all the details, or very fast model, but we lose a lot of information. Yeah? For some virtual platforms, this is okay. If you do not care so much about bandwidth and latency results, you just want to execute your software just to check if it runs, then this is also okay. No? But if you want to see the DRAM bandwidth or the latency, this does not make sense. But many people do not understand this. That's the problem. So you see a lot of research papers where people have chosen the wrong models to get results for their research questions, basically. Okay, so that's RTL. So you have your cycle accurate model and you use a clock. Yeah, so here you see the clock, and it's also pin accurate, so you have all the signals that you would have also in reality. And RTL models can have thousands of pins and simulate all events on all pins will make the simulation slow. Yeah, because you have to put that into the event queue, and we discussed that, delta cycling and all of this. So for example, if you implement an RTL bus system like AHB or something like that, you have 75 events that the SystemC kernel has to simulate. Yeah, so and for each bus access, you have to simulate these 75 events. So the question is, can we abstract something away without so much harming the timing accuracy? And this is the idea of transaction level modeling. So at the end in TLM, we are just interested basically when is data transmitted. And this is in the DDR bus, for example, here. There's the begin of a transmission and there's the end of a transmission. And then sometime later, there's again the start of a transmission and again the end of a transmission. And these are data packets that we see here. And this is actually what we model in TLM. So we model that some amount of data is transferred at a specific starting point and at a specific end point. And most importantly, we do not simulate any clocks, because a clock is a signal that has always a lot of events. Yeah? And even though at some points in time at this clock nothing happens because we just count up a counter or something like that, not much happens. We have to simulate this clock signal, and this will increase the wall clock time. So in TLM, we usually do not use a clock. And we reduce the structural accuracy by replacing signals by function calls. So we use the classical object-oriented concept that modules communicate with each other by using function calls. And in this function call, we put a pointer to this data packet. And we get rid of all these pins and signals. So we just communicate by function calls. And this is communication-centric. We concentrate only on the important events that matter. And we call these data packets basically transactions. And in TLM, a bus access has between 1 or 4 events, depending on how accurate you're simulating it. There is not only one TLM, there are several levels of TLM that you can do, so loosely timed, approximately timed. And this makes simulation fast. So in TLM, you can be 100 to 10,000 times faster compared to RTL. So it's really giving you a speed up of several orders of magnitude. Yeah, so how does it work in TLM? It's in SystemC pretty similar to that what we have seen already. But in general, we have again a producer, which is an initiator in TLM. And then we have a target that could be a memory. So this could be a CPU, this could be a memory. And the consumer is a hierarchical channel. So it's basically also implementing an interface that we can connect consumer and producer together. But internally also it derives from SC module, and also inside that there could be some threads that are running. And also this we want to build first. So I don't show you the actual SystemC concept of TLM right away. My goal is now again to implement in the last 15 minutes a custom TLM that you understand basically the idea. That's more important than directly diving into the actual code in SystemC. So, where we are. So, I think I just delete all of this. Well, maybe not everything. Just maybe keep the SC main there. But the rest can go, I guess. Okay. First of all, I want to introduce something that we call command. So each transaction will have a command of a specific type. So that could be a read command or could be a write command. And therefore I create an enum, which I call command. And that could be either read or write. So for memory, we could make a read access, or we could write something into memory, and then we would send a write command. And then I told you already that we have data packets that we send around. We will send around pointers. So this makes the simulation fast. We are not doing call, so we are doing call by reference and not basically the copy of data. So that's also the idea in TLM, to make simulation fast. And therefore we need the data packet, and this can be just a struct, which we call transaction. Transaction level modeling. We will send around transactions. And the transaction, will have a specific command. What else would you think a transaction would have? So now we can say, okay, this transaction we will send out, it is a read or a write. But what else do we need? What kind of information and also meta information?
Which ports are used?
No, the port is not important right now, but good remark. So we will send out this transaction on a specific port, and then it's implicitly clear. But if you make a DRAM access, what do you need?
Information, for example, the address of this.
Exactly. So we need an unsigned int, unsigned int with the address, for example. So let's assume we want to write to the DRAM something. What else do we need?
The content we want.
Exactly. So the actual payload, and I just also take now unsigned int. And I call that just data. So now we have our data packet with the actual data, but also with some metadata. Okay, so now we need again an interface, like we did it before. So we make now the so-called transaction interface, and this is now just our custom thing. And we derive again from SC interface, as we did that before. And now that's the main difference. We do not have anymore a read or a write method here on the interface. because we distinguish that now with the command in the transaction. So what we have here is now just that we have a so-called transport function. And I will just make it again pure virtual because it's just the interface. But there we give something. So here we put in the transaction, and we do not do the copy. Yeah, so the call by value, as this is called, we do always call by reference. So here we create a reference of this transaction object, and I just call it trans. And that's the main idea. So what we will do is we have now an initiator. Also that will have again the black port here. So this is the initiator, will be connected to our target. That could be, for example, the memory. And now we create somewhere in memory this transport object with our three things here. And then we create it inside the initiator, but we have then a pointer to this. And instead of copying this whole thing with a function call there, we just copy that pointer over there. Then we have the pointer here, and that points again back to this data structure. A pointer is just a 64-bit number that we send around, and not all this data and metadata that we could have here. And this makes the simulation fast. That's the main idea. So, I don't know if I have still enough time. Let me check. A little bit time I have, but I will not completely finish that. But I think tomorrow I will do again lecture. So tomorrow morning, when do we start there? 8:30, right? Yeah. So at 8:30 I will definitely continue that, but I will give you. Let's start and see how far we can go. So we will create an SC module, which is our initiator, and I call it again producer, because it can have any name. And that's pretty similar to that what we have seen so far. So there is SC port again, and now I use this transaction interface here. And I call that again output. So it's not much different to that what we have seen so far. And then I have the constructor again, producer. And I will also have again a process, same as we had before. And I will create an SC thread. That basically is this process here. And now our goal is for today, and tomorrow we make the consumer side as well. We want to send out a write command. So our producer here could be maybe a CPU. So maybe this is a CPU, and in the beginning of the simulation, the CPU will generate some writes for whatever reason, but we just assume that. So let's make a for loop. Just pretty simple, and we want to send out 4 transactions. So, yeah, and then we wait maybe for 1 nanosecond. And now we create a transaction. Transaction, trans. And now we have to fill in some meaningful metadata and data. So let's say trans.address, we just take the address of the for loop. So we count up the address by 1 every time. Yeah, so the data could be now any random number or any number, because I have defined here unsigned int. So I just put in there something. It could also be the address itself, whatever. It doesn't matter so much. So we have some data that we want to transfer. And then also there is the command that we have defined. No, I just called it command. And this will be now write. Okay? And now we have prepared this transaction. So we have a target address, we have the data, and it should be a write. And now we have to send out the transaction. So what we will do, probably you know it. So what is our interface? So our output port is here. How can I send out a transaction now? Yeah. Yeah. So I call this transport function output dot. No, it's in that sense it's a pointer. Therefore we have to use that operator. Transport. And what I'm missing still? What I'm still missing here? So like that, it would not work yet. So if you look on the interface again, what do you see here? Yeah.
Pointer.
Yeah, so this is basically the reference. So they use the reference here, so not pointers. So they use that way, but also it works. So we just put the transaction here. Yeah, so and that's the idea. So instead of modeling all these pins, we create a data packet that holds all the information that we usually transfer over these pins in an object. And this is, I think that is also what the people came up with the idea of object-oriented programming, that they send around objects also for communication. So that's basically that concept. Yeah. So that's basically what an initiator would do. And we can now also verify that. So we do the same for loop, but now we do not set any data. We create a transaction, we use the same address as before, and now we do a read. And then we could do send out this, and if we return from that function call, we will have the data because the memory will basically provide that. And what we can do then is we can then call sc assert, for example, and check if trans.data is equal to that what we actually wrote. So that's kind of a test. So we write something into the memory, and then later on we read it, and then we read if that's actually that is the data that we expect. Yeah. So yeah, we could also make the output here of that. So trans.data. Yeah. Okay. I think we will then continue tomorrow, yeah, with the other side. So, but let's very quickly jump, no, not here, again into that presentation. There. So that's basically the idea. Yeah. So we build a CPU and a memory, and tomorrow we will see then how basically this transaction flows around in the system. So we create this transaction here, and then we have the pointer, yeah, and we move the pointer around by calling functions. So each line here is again a function call where we pass the pointer, and this takes the pointer, checks then on the data something, decides to which output port it should go, pointer travels there, and we do not move a lot of data around, yeah? Because that would consume additional time. So we work with the pointers, and that's the main basic concept of TLM. And tomorrow we will check all these details and differences and different levels of TLM. And then I think the next week is probably only an exercise. There is no lecture. And then we have the Christmas break anyway, I guess. Yeah? So probably nobody will show up in that week of Christmas, I guess. Okay, all the schedule you will find also again on Campus. And then I would say let's see tomorrow again at 8:30 downstairs. Yeah?